All right, in this video we're going to look at the different forces that we will see in problems. The first type is a generic applied force, and this is anything that is said to be acting on the object that doesn't have a specific definition. All right, so this is more like a just a normal push or pull by your hand or other object. All right, and a push or a pull is really what the definition of a force is. It's the most basic way that we can say it. And that's it. So it doesn't have any particular specific properties there. If it's just an applied force, it's generic, and it is what it is. Then there is friction. We are all somewhat familiar with friction. Now, friction has a specific definition here. It is caused by a surface it acts parallel to the surface, and it opposes motion. And that type of motion, it would have to be sliding. All right. Now, it just has to act opposite the direction is actually moving, or the direction that it would tend to move. So here's different examples here. So here we have a block on a surface. This thing does have some velocity as it is sliding. However, we do have friction between the surface and the block that is going to oppose its motion. So we have the force of friction here, okay? And here it is moving. If we put a block on an incline, is it necessarily going to slide down the ramp? Depends on how steep the incline is and how sticky the surface is. But the object would tend to slide down the ramp, so the frictional force would have to be acting upwards to prevent that sliding. All right? So it's going to oppose the sliding motion. It does not have to actually be sliding for friction to be acting. Okay, the next force is the normal force. All right, normal force. In geometry, the word normal is perpendicular. So really this is the perpendicular force. All right, it is exerted. Let me make sure I'm on frame here. Exerted by a surface and acts perpendicular or normal, that says normal, to the surface. All right, so let's look here. We can have object on that surface. Well, normal force pushes this object. Now there's other forces here. So if the block is pushing down on the surface then has to push upwards on the object. And that would be the force of the surface on the block, and we would call that the normal force. Well, let's tilt the surface. Now we have a block sitting on a tilted surface. Well, the normal force still has to act at a 90 degree, okay, normal to the surface, Fn. If we have something pushing a block against a wall, well, the normal force will still be normal to the surface, all right? Always making a 90 degree angle with respect to that surface. All right, next one, tension. All right, tension is a force from a cord, string, rope, whatever, okay? And it always acts along the cord and always away. All right, so wherever side the cord is on, it has to be acting along that cord. All right, so here we have a block, could be on a surface, and then we have a cord there. You pick up the cord and you pull it. It's going to become taut, right? Tighten up the cord, and that is going to be the direction of your tension force. Right? Always has to act away. You can't push with a string. All right. Go ahead and try. See how that works out. All right. So that's tension force. Now we have one more force, which is weight. All right. Weight. Weight is the force of gravity. It is caused by the mass of the Earth. All right, so gravity is a field force, which means there actually doesn't have to be contact between the Earth and the object. All right, just like how magnets will repel or attract without actually being in contact. Same thing with positive and negative charges. They are field forces. When we're looking at weight of an object, it's going to act straight down because we are not zooming out so that we see the Earth as a sphere. We are looking as we see our surface currently. So straight line, okay, flat floor, unless you are a flat earther, and I don't know about that. All right, always acts straight down, technically towards the center of Earth or any planet, because all planets have gravity. Okay, so again, here we have a surface, we have a block on the surface. Guess where gravity is going to act? Gravity is going to act straight downward. Let's wordy it up here. Force of Earth on block. All right, really is what it is. All right, if we go out into deep space and we end up getting very, very far away from anything that has a significant amount of mass, we would get rid of gravity. If we have no gravity, we have no weight. But we can have mass. Mass doesn't disappear, right? Go to the moon. You weigh less. Your mass didn't change, right? So weight is not mass. Mass and weight are different. Weight is a product of mass, mass times, and I'm just going to say it's gravity, all right? Mass times gravity. So we can use different symbols for weight. It'll be either capital W, or it could be a force sub G for force of gravity. Doesn't matter which one you use. I'm going to usually use just this right-hand side anyway, where M stands for mass and G stands for gravity. It's a gravity constant. There was an Ed puzzle that kind of confused us on what G is equal to versus what the acceleration of gravity is equal to, where G was equal to positive 9.8 and acceleration of gravity was negative 9.8. Well, G is not a vector. It does not have direction to it. G is just a value of 9.8 meters per second squared. It is not a vector. It is just something that you multiply by the mass in order to get the actual amount of force that is being exerted by the Earth on the object. All right. So when I label these, I am probably just going to write mg, because we really got to make sure that we know that weight is always mg. It's not just mass. It's mass times gravity. Okay, so that's all the forces. So let's look at one more thing, and it's called free body diagrams. Free body. Okay, or some people just call them force diagrams. All right. What we're going to do is try to simplify our scenarios. So if it's just a block on a surface, it's not that bad. If we start having Spider-Man swinging and hang bad guys by multiple different webs, then it starts to get a little bit involved with the diagram here. So we would have to imagine it in a different way. A simple block sitting on a surface, we would have to draw out all of the forces that are acting on that block. And we're going to draw them all acting at the center of mass. We can really just pick one particle and treat this whole thing moving as one particle. Looks like my video froze for a second. Oh, there it goes, back. And hopefully that didn't screw everything up. All right, so on here, we always know that, well, we're on Earth here, and gravity is pulling that block to the surface. But block's not going through the surface. There is the surface holding the object upwards, and you would have the normal force. So there you go. That is a force diagram. To call it a free body diagram, you're basically just getting rid of all the details and just drawing the force arrows. That's it. So you erase the blue, you get a free body diagram. All right, they can get more complex. Let's tilt this, put the block on the surface, and it is motionless. It is just sitting there. How could it be sitting there? Well, it's not slippery enough to slide down the ramp. So there has to be other forces that are acting on it. Okay, we have gravity being pulled straight down. All right, just because the surface tilts does not mean the entire Earth tilts. So gravity is pulling that thing down. We have contact. All right, it is touching the surface. That means that the surface has to exert a force on the block. And actually, this surface exerts two different forces on this block. There is the perpendicular force, the normal force. And why is it not sliding down the ramp? We should know that there is a frictional force, and it's going to oppose the direction of where it wants to go, right? It wants to slide down, can't slide down because it's holding it back, right? And we will use a small script little f there to show friction, okay? Force diagram, have everything on there. If you wanted to just draw the free body diagram, again, dot, don't draw anything that's in the blue. You would just draw the forces in their directions. And what this really does is once we draw enough of them, you'll start to see that the surrounding of the object doesn't really matter for how you solve the problem. We can have many different scenarios that the arrows are looking like this. The forces might be different. These can be two different tensions. One could be a normal force, the other one can be a tension. And changing up the forces does not really change up how you solve the problem. It's just what is it actually in contact with. So we will get a lot more practice drawing these free body diagrams. They are the most important part of solving force problems. So we have to make sure we can do that accurately, and we'll probably do that more in class.